So as we get started here, we will do this as a review. We have a car that's merging, and it hits the other car, and this will be a perfectly inelastic collision, where they'll stick together, and you want to find out what the resultant would be, whether the resultant velocity. So in this one here, the car 2 is going at an angle. Car 1 is just going to the east. And so we talked about how important it is to look at the momentums in the x and y and work those out separately. So if you remember what we got to do, we got to break up our force into the x and y values, and we can get our x and y velocities. And then from there, we can look at the momentum in the x and y separately and get the resultant. So go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. All right, so we have our x velocity, we have our y velocity, the car's hit, and for the x, what we're dealing with is the car 1 is going in the eastern direction, 17 meters per second, and then car 2 is going at 16.383 meters per second in the x direction, just using the x component. And so we can find the final velocity, which is going to be the same for both cars. We add up the masses, and we should get 16.67 meters per second as the resultant. Now, for the y, we're dealing with, car 1 is going in the x, and we have car 2, and yeah, so for this one, the key is going to be seeing how mass 1, car 1 is not moving in the y at all initially. So the initial velocity in the y is 0 for car 1. For car 2, it's 11.472. And then we can find the final velocity, the resultant velocity of both. And we end up getting 6.0945 meters per second. And then we can get the resultant, which is 16.67 and 6.0945. We get the resultant as 17.75 meters per second at 20.1 degrees north of east. That will be the final momentum of those two cars if they hit and collide and stick together and go off at that angle. And then the momentum will be 56,798. We just take that final velocity and multiply it by the two masses. All right, so work is the quantity that describes the displacement of an object times the force parallel to the displacement, and we end up getting a Newton meter for this of work, or that turns into be a joule. One of the questions we need to address is work a vector or scalar? It is a scalar. If force is moving in the direction which it acts, work is done. The work is a process of converting energy, and it's an energy's ability to do work, and so it is a scalar. There's no direction with that. All right, so let's go ahead and try this one here. A man lifts a 50-kilogram box 2 meters into the air. How much work does he do on the box? So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so we should get 980 joules or Newton meters. The force is up, the displacement is up, so it's cosine of 0. So force is up, displacement is up. This is cosine of 0 degrees. We have our 2 meters vertically going up, and then we have our force 490 newtons, and we get a total of 980 Newton meters or joules of work. Here, a man holds a 50-kilogram box at arm's length for 2 hours, walks 1 kilometer forward. How much work does he do on the box? So go ahead and pause the clip and do this one. And ready to check. You can hit play to continue. All right, so this is the classic example where you have a force going straight up. The displacement is at a 90-degree angle. Therefore, there is no work done. Even though they're exerting a lot of energy within their muscles and everything, there's no mechanical work done. All right, so this is a good one to review as well here. Joe pushes a box, slides across the floor at 3 meters per second. The coefficient of friction is 0.5. How much work does Joe do if he pushes the box for 15 meters? And then part B, how much work does friction do? So go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. All right, so for this one, we should set up the sum of the forces. It's going at a constant speed of 3 meters per second. So therefore, the force applied and force of friction are balanced. The force of friction, therefore, is the coefficient times the normal force, which is 49 newtons. And so we have the work, which is 49 newtons times 15 meters, and we get a work of positive 735 joules. And for friction, how much work does friction do? That's cosine of 180. So, the displacement's to the right, friction is to the left, so therefore a cosine of 180 degrees, and it would be the equivalent of the other one, but just negative work. One of the things that's really critical, right, as we take a look at work is the factor where if you have a force displacement graph, you can find, if you get the area, you can find the work. So we know work equals force times displacement. Two things are being multiplied, and we can get the area and of a force displacement graph and get the work. So this is similar to where, you have a velocity time graph and you get the area. We know velocity equals delta x over t. V times t is delta x. So therefore, we're multiplying velocity, which is on the y, and time on the x, and we can get the area, which is similar to what we just did here with work. And then if it's a variable amount of force, what we can do is we can break up the graph into parts, and so we can get that there and that amount there. We can get the the triangle area, and then we can get this area as well. And yeah, and we should be able to do that, and we'll get practice with that here. So for this one, how much work is done when an object acts or forces on an object and pushes it from 0.25 to 0.75 meters. So go ahead and pause the clip and do this one, and we're ready to check. You can hit play to continue. All right, so from 0.25 to 0.75 meters, it's going to be 0.1 joules and 0.2 joules, so a total 0.3 joules of energy on this object here. How about this one where the force is going up and then the force decreases, and we push this, and we want the work done from 2 meters to 4 meters. So go ahead and pause the clip and do this one, and we're ready to check. You can hit play to continue. All right, so you should get somewhere close to 0.63 joules. You got the height here, you've got the length down here, so you can get the area, and that's how much work is done from there to there. Remember kinetic energy, right? Energy due to motion, 1/2 mv squared. We get our energy in joules. There's no direction with kinetic energy. It's a scalar. For potential energy, with gravitational potential energy is mgh. For mass, it's in kilograms, acceleration meters per second squared, and then height is in meters. For springs, it's 1/2 kx squared, whereas k is the spring constant, and then x is the displacement from equilibrium in meters. And then if you remember with work, the work energy, kinetic energy theorem, where the net work will equal the change in kinetic energy of a system, and the net work is the total amount of work, and then kinetic energy is kinetic energy final minus initial, and we can get that. So let's practice this one here. Joey kicks a stationary soccer ball with a force of 120 newtons. Coefficient of friction is 0.12 meters. His foot is in contact with the ball for 4 centimeters. What is the final velocity of the soccer ball? So yeah, go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so we can get the net force. So we have force applied forward is 120 newtons. The force of friction is the coefficient times the normal force. So the net force is 119.53 newtons, and the displacement is 0.04 meters. And we have our final kinetic energy minus initial. The initial is 0. It's starting from rest. And so the final speed will be 4.889 meters per second. Now, we also look at one of the most important equations here with non-conservative work. We have a car here that's traveling, slams on its brakes, and skids. And we want to find out D. How far did it go? Well, there's friction here, and that's really the only force that we're going to concentrate on. There's the force of friction back, displacements to the right. So we have non-conservative work, and we can set up the kinetic energy translational plus kinetic energy rotational plus potential energy gravitational plus potential energy spring. Now, there's no rotational, the car's not going to be spinning, you know, or not anything like that, so we don't need to worry about that. There's no height change, there's no springs involved. So all we're dealing with is translational kinetic energy change. Now, remember, non-conservative work is the force friction here times displacement times cosine of, well, the car's going to the right, the friction is to the left, so it's cosine of 180. And equals 1/2 mv final squared minus 1/2 mv initial squared. And you can find, yeah, how far does it travel without the mass. And so you should be able to do that, because with friction, you should be able to work that out. So go ahead and, yeah, complete that. And when you're ready to check, you can hit play to continue. All right, so we should get 160.256 meters is how far this will skid as it goes across. And so it's not a whole lot of friction there as it skids to a stop.